A suspension bridge is a type of bridge in which the deck is hung below suspension cables on vertical suspenders. The first modern examples of this type of bridge were built in the early 19th century. Simple suspension bridges, which lack vertical suspenders, have a long history in many mountainous parts of the world. This type of bridge has cables suspended between towers, plus vertical suspender cables that carry the weight of the deck below, upon which traffic crosses. This arrangement allows the deck to be level to arc upward for additional clearance. Like other suspension bridge types, this type often is constructed without falsework. The suspension cables must be anchored at each end of the bridge, since any load applied to the bridge is transformed into a tension in these main cables. The main cables continue beyond the pillars to deck level supports, and further continue to connections with anchors in the ground. The roadway is supported by vertical suspender cables or rods, called hangers. In some circumstances, the towers may sit on a bluff or canyon edge where the road may proceed directly to the main span. Otherwise, the bridge will usually have two smaller spans, running between either pair of pillars and the highway, which may be supported by suspender cables or may use a truss bridge to make this connection. In the latter case, there will be very little arc in the outboard main cables. History. The earliest suspension bridges were ropes slung across a chasm, with a deck possibly at the same level or hung below the ropes such that the rope had a catenary shape. Precursor of the Tibetan saint and bridge builder Thangton Gyalpo originated the use of iron chains in his version of simple suspension bridges. In 1433, Gyalpo built 8 bridges in eastern Bhutan. The last surviving chain-linked bridge of Gyalpo's was the Thangton Gyalpo Bridge in Duksam en route to Trashy Yangtse, which was finally washed away in 2004. Gyalpo's iron chain bridges did not include suspended deck bridge, which is the standard on all modern suspension bridges today. Instead, both the railing and the walking layer of Gyalpo's bridges used wires. The stress points that carried the screed were reinforced by the iron chains. Before the use of iron chains, it is thought that Gyalpo used ropes from twisted willows or yak skins. He may have also used tightly bound cloth. The first design for a bridge resembling the modern suspension bridge is attributed to Croatian polymath Fausto Veranzio, whose 1595 book Macana Novaya included drawings both for a timber and rope suspension bridge, and a hybrid suspension and cable-stayed bridge using iron chains. The first American iron chain suspension bridge was the Jacobs Creek Bridge in Westmoreland County, Pennsylvania, designed by inventor James Finley. Finley's bridge was the first to incorporate all of the necessary components of a modern suspension bridge, including a suspended deck which hung by trusses. Finley patented his design in 1808 and published it in the Philadelphia Journal, The Portfolio, in 1810. Early British chain bridges included the Dryborough Abbey Bridge and 137 metres Union Bridge, with spans rapidly increasing to 176 metres with the Menai Bridge, the first important modern suspension bridge. The Clifton Suspension Bridge is one of the longest of the parabolic arc chain type. The current Marlow Suspension Bridge was designed by William Tierney Clark and was built between 1829 and 1832, replacing a wooden bridge further downstream which collapsed in 1828. It is the only suspension bridge across the non-tidal Thames. The Széchenyi Chain Bridge, spanning the River Danube in Budapest, was also designed by William Clark, and it is a larger-scale version of Marlow Bridge. Wire cable. The first wire cable suspension bridge was the Spider Bridge at Falls of Schuylkill, a modest and temporary footbridge built following the collapse of James Finley's nearby chain bridge at Falls of Schuylkill. The footbridge's span was 124 meters, although its deck was only 0.45 meters wide. Development of wire cable suspension bridges dates to the temporary simple suspension bridge at Annonay built by Mark Seguin and his brothers in 1822. It spanned only 18 meters. The first permanent wire cable suspension bridge was Guillaume Henry Dufour's Saint-Antoine Bridge in Geneva of 1823, with two 40 meters spans. The first with cables assembled in mid-air in the modern method was Joseph Chailly's Grand Pont suspender in Fribourg in 1834. In the United States, the first major wire cable suspension bridge was the wire bridge at Fairmount in Philadelphia, Pennsylvania, designed by Charles L.A. Jr. and completed in 1842. It had a span of 109 meters. L.A.'s Niagara Falls suspension bridge was abandoned before completion. It was used as scaffolding for John A. Roebling's double-decker railroad and carriage bridge. The Ottobeit Bridge was the first modern suspension bridge outside the United States built with parallel wire cables. Structural behavior. Structural analysis. The main forces in a suspension bridge of any type are tension in the cables and compression in the pillars. Since almost all the force on the pillars is vertically downwards and they are also stabilized by the main cables, the pillars can be made quite slender, as on the Severn Bridge on the Wales-England border. In a suspended deck bridge, cables suspended via towers hold up the road deck. The weight is transferred by the cables to the towers, which in turn transfer the weight to the ground, assuming a negligible weight as compared to the weight of the deck and vehicles being supported. The main cables of a suspension bridge will form a parabola. One can see the shape from the constant increase of the gradient of the cable with linear distance. This increase in gradient at each connection with the deck providing a net upward support force, combined with the relatively simple constraints placed upon the actual deck. This makes the suspension bridge much simpler to design and analyze than a cable-stayed bridge, where the deck is in compression. Advantages: longer main spans are achievable than with any other type of bridge. Less material may be required than other bridge types, even at spans they can achieve, leading to a reduced construction cost. Except for installation of the initial temporary cables, little or no access from below is required during construction. For example, allowing a waterway to remain open while the bridge is built above may be better able to withstand earthquake movements than heavier and more rigid bridges. Bridge decks can have deck sections replaced in order to widen traffic lanes for larger vehicles or add additions width for separated cycling, pedestrian paths. Disadvantages: considerable stiffness or aerodynamic profiling may be required to prevent the bridge deck vibrating under high winds. The relatively low deck stiffness compared to other types of bridges makes it more difficult to carry heavy rail traffic where high concentrated live loads occur. Some access below may be required during construction to lift the initial cables at a lift deck units. This access can often be avoided in cable-stayed bridge construction. Variations: underspanned. In an underspanned suspension bridge, the main cables hang entirely below the bridge deck, but are still anchored into the ground in a similar way to the conventional type. Very few bridges of this nature have been built, as the deck is inherently less stable than when suspended below the cables. Examples include the Pont des Bergues of 1834, designed by Guillaume Henry Dufour, James Smith's Micklewood Bridge, and a proposal by Robert Stevenson for a bridge over the River Armon near Edinburgh. Roebling's Delaware Aqueduct consists of 3 sections supported by cables. The timber structure essentially hides the cables, and from a quick view, it is not immediately apparent that it is even a suspension bridge. Suspension cable types. The main suspension cable in older bridges was often made from chain-linked bars, but modern bridge cables are made from multiple strands of wire. This contributes greater redundancy. A few flawed strands in the hundreds used pose very little threat, whereas a single bad link or eye-bar can cause failure of the entire bridge. Another reason is that as spans increased, engineers were unable to lift larger chains into position, whereas wire strand cables can be largely prepared in mid-air from a temporary walkway. Deck structure types. Most suspension bridges have open truss structures to support the roadbed, particularly owing to the unfavorable effects of using plate girders, discovered from the Tacoma Narrows bridge collapse. Recent developments in bridge aerodynamics have allowed the reintroduction of plate structures. In the picture of the Yichang Bridge, note the very sharp entry edge and sloping undergirders in the suspension bridge shown. This enables this type of construction to be used without the danger of vortex shedding and consequent aeroelastic effects, such as those that destroyed the original Tacoma Narrows Bridge. Forces. Three kinds of forces operate on any bridge: the dead load, the live load, and the dynamic load. Dead load refers to the weight of the bridge itself. Like any other structure, a bridge has a tendency to collapse simply because of the gravitational forces acting on the materials of which the bridge is made. Live load refers to traffic that moves across the bridge as well as normal environmental factors such as changes in temperature, precipitation, and winds. Dynamic load refers to environmental factors that go beyond normal weather conditions, factors such as sudden gusts of wind and earthquakes. All three factors must be taken into consideration when building a bridge. Use other than road and rail. The principles of suspension used on the large scale may also appear in contexts less dramatic than road or rail. Bridges. Light cable suspension may prove less expensive and seem more elegant for a cycle footbridge than strong gird supports. An example of this is the Nesho Bridge in the Netherlands, where such a bridge spans a gap between two buildings. There is no need to construct special towers, as the buildings can anchor the cables. Cable suspension may also be augmented by the inherent stiffness of a structure that has much in common with a tubular bridge. Construction sequence. Typical suspension bridges are constructed using a sequence generally described as follows. Depending on length and size, construction may take anywhere between a year and a half up to as long as a decade. Where the towers are founded on underwater piers, caissons are sunk in any soft bottom is excavated for a foundation. If the bedrock is too deep to be exposed by excavation of the sinking of a caisson, pilings are driven to the bedrock or into overlying hard soil, or a large concrete pad to distribute the weight over less resistant soil may be constructed. First, preparing the surface with a bed of compacted gravel. Such a pad footing can also accommodate the movements of an active fault, and this has been implemented on the foundations of the cable-stayed Rio-Anti-Rio Bridge. The piers are then extended above water level, where they are capped with pedestal bases for the towers. Where the towers are founded on dry land, deep foundation excavation or pilings are used. For the tower foundation, towers of single or multiple columns are erected using high-strength reinforced concrete, stonework, or steel. Concrete is used most frequently in modern suspension bridge construction due to the high cost of steel. Large devices called saddles, which will carry the main suspension cables, are positioned atop the towers, typically of cast steel. They can also be manufactured using riveted forms, and are equipped worked with rollers to allow the main cables to shift under construction and normal loads. Anchorages are constructed, usually in tandem with the towers, to resist the tension of the cables and form as the main anchor system for the entire structure. These are usually anchored in good quality rock, but may consist of massive reinforced concrete deadweights within an excavation. The anchorage structure will have multiple protruding open eye bolts enclosed within a secure space. Temporary suspended walkways, called catwalks, are then erected using a set of guide wires hoisted into place via winches positioned atop the towers. These catwalks follow the curve set by bridge designers for the main cables, in a path mathematically described as a catenary arc. Typical catwalks are usually between 8 and 10 feet wide, and are constructed using wire grates and wood slats. Gantries are placed upon the catwalks, which will support the main cable spinning reels. Then, cables attached to winches are installed, and in turn, the main cable spinning devices are installed. High-strength wire is pulled in a loop by pulleys on the traveler, with one end affixed at an anchorage. When the traveler reaches the opposite anchorage, the loop is placed over an open anchor eye bar. Along the catwalk, workers also pull the cable wires to the desired tension. This continues until a bundle, called a cable strand, is completed, and temporarily bundled using stainless steel wire. This process is repeated until the final cable strand is completed. Workers then remove the individual wraps on the cable strands, and then the entire cable is then compressed by a traveling hydraulic press into a closely packed cylinder and tightly wrapped with additional wire, to form the final circular cross-section. The wire used in suspension bridge construction is a galvanized steel wire that has been coated with corrosion inhibitors. At specific points along the main cable, devices called cable bands are installed to carry steel wire ropes called suspender cables. Each suspender cable is engineered and cut to precise lengths, and are looped over the cable bands. In some bridges, where the towers are close to or on the shore, the suspender cables may be applied only to the central span. Early suspender cables were fitted with zinc jewels and a set of steel washers, which formed the support for the deck. Modern suspender cables carry a shackle-type fitting. Special lifting hoists attached to the suspenders from the main cables are used to lift prefabricated sections of bridge deck to the proper level, provided that the local conditions allow the sections to be carried below the bridge by barge or other means. Otherwise, a traveling cantilever derrick may be used to extend the deck one section at a time, starting from the towers and working outward. If the addition of the deck structure extends from the towers, the finished portions of the deck will pitch upward rather sharply, as there is no downward force in the center of the span. Upon completion of the deck, the added load will pull the main cables into an arc mathematically described as a parabola, while the arc of the deck will be as the designer intended, usually a gentle upward arc for added clearance if over a shipping channel, or flat in other cases such as a span over a canyon. Arched suspension spans also give the structure more rigidity and strength. With completion of the primary structure, various details such as lighting, handrails, finish painting and paving are installed or completed. Longest spans. Suspension bridges are typically ranked by the length of the main span. These are the 10 bridges with the longest spans, followed by the length of the span and the year the bridge opened for traffic. Akashi Kaikyo Bridge, 1,991 meters, 1998. Human Bridge, 1,650 meters, 2009. Great Belt Bridge, 1,624 meters, 1998. Osman-Ghazi Bridge, 1,550 meters, 2016. Yesunsin Bridge, 1,545 meters, 2012. Runyang Bridge, 1,490 meters, 2005. Fourth Nanjing Yangtze Bridge, 1,418 meters, 2012. Humber Bridge, 1,410 meters, 1981. Jiangyin Suspension Bridge, 1,385 meters, 1997. Hardanger Bridge, 1,380 meters, 2013. Singma Bridge, 1,377 meters, 1997. Other examples: Union Bridge, the longest span from 1820 to 1826. The oldest in the world still in use today. Roebling's Delaware Aqueduct, the oldest wire suspension bridge still in service in United States. John A. Roebling Suspension Bridge, then the longest wire suspension bridge in the world at 1,057 feet main span. Brooklyn Bridge, the first steel wire suspension bridge. Bear Mountain Bridge, the longest suspension span from 1924 to 1926. The first suspension bridge to have a concrete deck. The construction methods pioneered in building it would make possible several much larger projects to follow. Ben Franklin Bridge replaced Bear Mountain Bridge's longest span at 1,750 feet between the towers. Includes an active subway line and never used trolley stations on the span. San Francisco-Oakland Bay Bridge. This was once the longest steel high-level bridge in the world. The eastern portion has been replaced with a self-anchored suspension bridge which is the longest of its type in the world. It is also the world's widest bridge. Mackinac Bridge, the longest suspension bridge between anchorages in the Western Hemisphere. Sea-Doo River Bridge, the highest bridge in the world, with its deck around 500 meters above the surface of the river. Notable collapses: Silver Bridge, Point Pleasant, West Virginia. I-Bar Chain Highway Bridge, built in 1928, that collapsed in late 1967, killing 46 people. Tacoma Narrows Bridge, 853 meters, 1940. The Tacoma Narrows Bridge was vulnerable to structural vibration in sustained and moderately strong winds due to its plate girder deck structure. Wind caused a phenomenon called aeroelastic fluttering that led to its collapse only months after completion. The collapse was captured on film.